Hi girls. The lesson we're going to be covering today in this video is lesson 2.6.2. Now this is one of the first times that I'm using this to make a video, and as I start to write you'll notice that when the pen scratches across my screen it makes a noise. I haven't figured out how to stop that yet, but hopefully in the future I will. So when you hear that noise, that's what's going on. So on Friday we did section 2.6.1, and that was where we compared two linear functions together. We took a look at both of their y-intercepts and compared them. We took a look at their rates of change, and since they were linear, that would be the slope of each of them, and made a comparison between those. Sometimes we had an equation, sometimes we had a graph, sometimes we had a table, and sometimes we had a problem in context. We're going to extend those same exact ideas into exponential functions today. So the first thing I want you to do, if you have your workbook at home, is go get your workbook. So you can pause the video and go get your workbook. And we need to get to page 161 and 163. If you don't have your notebook, don't worry about that. I've got the problems here on the smartboard. We're going to do the guided practice problems, example 1, 2, and 3. So you could have followed along with me. If you don't have your workbook page, then get out just a piece of notebook paper and write down page 160, workbook page 161, example 1. So pause the video, get yourself ready, and then come back and we'll start working the problem. All right, so example 1 says, compare the properties of each of the following two functions over the interval 0, 16. Once again, we have two functions given to us in two different formats, except this time they're exponential functions. And we are going to compare the exact same two things. So when we compare our functions, this isn't writing. There we go. When we compare our functions, we are going to do the same thing we did before, which is we are going to compare the y-intercepts. You can hear the noise it's making, right? And the rate of change. So the first thing we're going to do with this one, we have two exponential functions. I can tell that by my graph, because it's not a linear graph. If I look at my table, I notice my x values are going up by 4 each time, but my y values are going up by something different each time. So I know I have two exponential functions. So the first thing we're going to compare is or look at the y-intercept for function A. All I need to do is come over here and look at where function A crosses the x-intercept. And since this seems to be this is going up by 100ths, it appears to be about halfway. So for function A, f of x, I'm going to say that its y-intercept is 0, 850. Fortunately, for function B, I can just look at my table, and I notice that my y-intercept is right here. So for g of x, my y-intercept is also 0, 850. So these two functions have the same y-intercept. We've done that comparison. The next thing we need to look at is the rate of change over a specified interval. So let me just get rid of these lines here. So the interval that I need to use is when x is 0 and when x is 16. So let's start with the table because it's easier to work with the table at first. Function B. So I need to look at when x is 0 and when x is 16. So the 2 points I need to use my slope formula with are 0 850, and 16, 1,480.88. So now I just need to use my slope formula, which says y sub 2 minus y sub 1 over x sub 2 minus x sub 1. I don't know why that box is there. And in this case, those numbers are, oops, I forgot the 0 here. 1, 4, 8, 0.88 minus 850 over 16 minus 0. After I do all the math in my calculator, I get 39.42 for my rate of change for g of x. Now I need to actually come over to my graph for f of x, and I have to find the interval between when x is 0 and when x is 16. And we already said that our y-intercept was 0, 850. And now we need to look at the graph when x is 16. So I move up, and it's right here. So when x is 16, well, g of x, or f of x in this case, is 1600. So these are the 2 points that I need to use. I'm going to switch colors. When using my slope formula. So y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Oops. I don't know why that's coming with me. Sorry, girls. Equals, in this case, 1600 minus 850 over 16 minus 0. And in this case, after the mathematics, it's my calculator, I get 46.875. So when I made my 2 comparisons, I found that my y-intercept was the same. So I'd say both functions have the same y-intercept, and when I look at my 2, this is f of x, rates of change, I would say f of x has a greater rate of change over the interval. And you have to mention over the interval, because at some other point on the 2 graphs, there may be a different rate of change. So this is how we would answer example 1. Let's turn to example 2. In example 1, we had a table and a graph. In example 2, we have a problem in context and a graph. So here it says a petri dish contains 8 bacteria that double every 15 minutes. Compare the properties of the function that represents this situation to another population of bacteria graphed below that starts with 8 organisms over the interval 150 to 210. So in this case, if I want to compare my y-intercepts first, if I look at the situation that I'm given, I can write the equation for my scenario if I want to. So my equation, it's exponential, would be y, let's use f of x. I think I'll keep it smaller. We're going to use f of x is equal to 8, which is my starting amount. It's going to double, but it's going to double every 15 minutes. So I don't raise it to the 15, but I raise it to the x over 15. My y-intercept is where it starts, and the context of the problem tells me that it starts at 8. So in this case, my y-intercept is 0, 8. On my graph, it looks like my y-intercept is somewhere close to 0. It's hard to tell, though, on this graph. But we have to look back up in the problem because it tells us that this scenario also starts with 8 organisms. So on the graph, we also have a y-intercept of 0, 8. So once again, both of these functions have the same y-intercept. Let's take a look at their rates of change. The interval over which we need to look at their rate of change is 150 to 210. So let's start on the graph this time. Let's look at 150, which is right here for my x value. When I look at my graph, that point is right here. And these are going up by 200, and that isn't really 300. I'm going to say that's maybe 250. So the point that I'm going to pick for the graph to find the rate of change is going to be 150, 250. And then my next part of the interval is at 210, and that looks like it's at 1,000. So these are my 2 points that I need to use. So I just use my slope formula again, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And in this case, that gives me 1,000 minus 250 over 210 minus 150, which gives me 750 over 60, which gives us a rate of change of 12.5. Now I need to go back to my blue function, f of x, and determine, let me rewrite it down here so we can see it, equals 8 times 2 raised to the x over 15. And I'm still looking at the interval from 150 to 210. So first I find f of 150. Which is 8 times 2 to the 10th, which gives me 8,192. Next, I need to find f of 210. So that's 8 times 2 raised to the 210 divided by 15. And in this case, that's 8 times 2 raised to the 14th, which gives us 131,072. So the 2 points I need to use here are 150, 8,192, 210, 131,072. So this is what I'll use in my slope formula. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. In this case is 131,072 minus 8,192 over 210 minus 150. And after I do all the math for that, I get 122,880 over 60, do the division, and it becomes 2,048. So what was our rate of change here? Our graph, it was 12.5. For our function, it was 2,048. So in this case, we would state that both functions have the same y-intercept, and our blue function in this case, which was our function in context, and the function in context has the greater rate of change. All right, last problem. Problem 3. Another pendulum problem. We've had this one before. A pendulum swings to 90 degrees of its previous height. Pendulum A starts at a height of 50 centimeters. Its height at each swing is modeled by the function f of x is equal to 50 times 0.9 raised to the x. The height after every fifth swing of pendulum B is recorded in the following table. Compare the properties of each function over the interval 5, 15. So right away, I see my y-intercept for g of x. Is 0, 100. And in the context of the problem for pendulum A, it starts at a height of 50. So I know for f of x, pendulum A, that's A, the table is B, I start at 0, 50. So that means I already know that pendulum B has a higher y-intercept. The next thing we need to do is compare these two over the interval of 5, 15. So I need to pick this point and this point. So for pendulum B, using the slope formula y sub 2 minus y sub 1 over x sub 2 minus x sub 1, I take 20.59 minus 59.05 over 15 minus 5. And when I do that in my calculator, I get negative 3.846. The next thing I need to do is work on f of x. I have a 1 point, or I don't have, I can't use my y-intercept. The 2 points I need to use are on the intervals when x equals 5 and when x equals 15. So the first thing I need to do, let's rewrite our function f of x is equal to 50 times 0.9 to the x. And I need to find f of 5 to get my first point. So I plug in 5 for x, and I get 29.52. So my first point is 529.52, and then I need to find f of 15. what y value do I get when I plug in 15 for x? And for this, I get 10.29. So the second point in my interval, the other endpoint, is 10.29. So again, slope formula, y sub 2 minus y sub 1 over x sub 2 minus x sub 1 gives us 10.29 minus 29.52 over 15 minus 5. And that answer gives me negative 1.923. So my first rate of change, this is pendulum B, compared to my second rate of change, pendulum A, shows that pendulum A slows down, or is it was at a slower rate of change than pendulum B. So how would we answer our question? First of all, we would say that the y-intercept, I don't know why it keeps doing that, the y-intercept of g of x is greater than the y-intercept of f of x. We saw that earlier. What does that mean in context? It means that pendulum B starts out at a higher distance. It starts at a greater height. And as far as our rates go, pendulum A, or pendulum B, is losing height faster. Pendulum B has a higher rate of change, so it is losing height faster than pendulum A. All right, so those are the three problems that I wanted us to do together today. This will help us when we get into class tomorrow. I expect that you've done these problems with me either in your workbook pages or on a separate notebook page. So you need to have those prepared to show me on Tuesday. And then when we get together, we'll just start working some problems. And then the final thing we're going to do on Tuesday is we're going to take linear functions and exponential functions and then compare the properties of the two of those. So instead of linear to linear and exponential to exponential, we'll start looking at how do we compare linear functions to exponential functions. All right, so enjoy the rest of your weekend, girls, and I will see you on Tuesday.